Good, the numbers are ticking up here. We're up to 35 attendees, plus our panelists makes it 45. So it is 10 o'clock. I'll just go through a few of the rules and things here. I realize that the number is going to keep going up here. We probably should hit 60 or 70 here fairly quickly. I just thought I'd mention that this is the 6th webinar PTRC has put on since last May. We decided to start to put on webinars during the COVID crisis. That was one of the motivating factors, and we've been ongoing over the last 6 now in about a year. This is the first webinar that we've done, though, with our partners who are actually right next door to us here at the Innovation Research Park at the University of Regina, the International CCS Knowledge Centre. We have worked closely with them in the past on a number of things, but we have not had a joint webinar, and we felt it was time. So that was one of the motivating factors in doing this particular project. Now, there will be 4 presenters today. The total webinar length will be around 75 minutes. 60 minutes of that will be presentations. The last 15 minutes will be a Q&A session. Now, the Q&A session is going to be done via typing in questions. If those of you who are on your screens, if you scroll to the bottom or you just put your cursor to the bottom, you'll see that there's a Q&A feature there. You open that and you would type in any questions that you have during any of the presentations into that. If the question is easily answered, typed answers, I may do that. If they're a little more detailed, we will flag them and hopefully get to them in the session at the end. The final 15 minutes will be Q&A. If we don't get to it in that short 15-minute period, that's why I'd like you to use the Q&A section or the Q&A feature, because they end up going into an Excel spreadsheet that gets generated right after this meeting, which I can then share with all of our speakers, and they may choose, hopefully will choose, depending on the question, to send you an email that answers your question and perhaps start a dialogue with you if it's particularly important. So please do use the Q&A feature. You can use the chat to communicate with me. You can't communicate with each other, which is another option for putting a question, but those are a little harder to track because sometimes there can be a number of things happening in the chat feature. So please do use the Q&A feature. Secondly, or thirdly, I guess, this webinar will be posted after it is recording right now, just so that you're all aware, this is a recorded webinar. It will be featured at the PTRC YouTube page. It will also be offered to the Knowledge Centre if they choose to stream it as well, either on their YouTube page, I'm not sure if they have one actually, or at their website. There'll have to be a bit of editing at the beginning and at the end, which will take me probably till Friday or Monday to get it up, but it will be up and you will be notified via email when it's up. And I think finally, when you sign off from this, whether you do it halfway through the webinar, if it's not to your taste, or if you do it at the end, there will be a survey. It's a very brief survey that comes up on your screen. It'll be about 5 questions. I think 4 of them are just simply click yes or no. One of them is actually asking you to type a few words if you have anything of interest to say. And so that is really what we're looking at in terms of signing off. So that being said, I'll just say a few things about our speakers today. Most of the bios, as you saw when you registered for this, are contained at the registration site. So I'm not going to go into detail. I am just going to mention that our first 2 speakers are from the International CCS Knowledge Centre. We have Beth Hardy, who is Vice President of Strategy and Stakeholder Relations at the International CCS Centre, and we have Conway Nelson, who is Vice President of Project Development and Advisory Services. Those will be our first 2 speakers. There'll be a slight pause, and then the next 2 speakers will be Eric Nickel, who is Director of Operations at the Petroleum Technology Research Centre, and Jing Zhao, who is a Manager of Disposal Well and Storage Projects at the Research Management Branch of the Energy and Regulatory Division of the Ministry of Energy and Resources with the Government of Saskatchewan. And I'm really looking forward to that presentation because I have not seen one yet from the Ministry of Energy and Resources, at least not for about a year. We used to get more regular presentations from them, but we haven't had one from them in a little while. So that's my brief introduction. I will now turn it over to Dan Mclean, who will welcome everybody. Dan, go ahead.
Thank you, Norm. Thanks for going through all of that. My name is Dan Mclean. I'm the president of the Petroleum Technology Research Centre, and thank you for attending our series of webinars. These are important for us because they allow us to share with you the kinds of things that we're doing at the PTRC, but also the things that we're doing in collaboration with a lot of other organizations, and especially at this time with such an elevated interest in carbon capture, utilization, and storage. I'd like to, first of all, acknowledge that the PTRC is located next to the University of Regina in the Innovation Place building, which also houses the CCS Knowledge Centre. Now, we're situated on Treaty 4 lands with the presence of Treaty 6, and these are the territorial lands of the Nihiawak, the Anishinaabeg, Nakota, Lakota, Nakota, and homelands of the Métis Nations. So I think that's important to acknowledge as we go forward here. So you want to do a CCS project in Canada. Well, this is the place to hear about that. Now, there have been a number of webinars that I've attended on this topic. What is unique about this webinar is you're going to hear from folks who have been involved in this, who are doing projects or have done projects in this area already. This is direct experience that you're going to hear from folks from the Knowledge Centre and from the PTRC. And I'd like to take this opportunity in advance to thank the Knowledge Centre, Beth Valiaho and Conway Norman for attending, as well as I'd like to thank the Ministry of Energy and Resources for also being a part of this. So you're going to hear from Beth Valiaho, and she's going to speak to a number of the challenges associated with putting together a business case for CCUS, in particular around issues around government support that is certainly going to be required for this. Conway is going to speak about the carbon capture technologies associated with this challenge. And then Eric Nickel from the PTRC will speak to CO2 storage, in particular geologic storage, which is the expertise of the PTRC over the last 23 years, whether through sequestration in the Weyburn CO2 EOR project or Aquastore, which is the deep saline storage project that the PTRC operates. So you're going to hear from people who know what they're talking about. So that is what's unique here. And so without any further ado, I'll turn it back over to Norm Sakuda. But one more thing, I have to make a plug. The PTRC is the owner of the Williston Basin Conference, and that is going to be held in May 2022 in Regina. We're hoping this COVID thing will be behind us and that you will be able to travel to this, where you will hear from direct experts on this continuing area of carbon capture, utilization, and storage. So with that, I will turn it back to Norm.
Okay, thank you, Dan. Go ahead, Beth. You're welcome to share your screen and to begin your presentation. Thanks.
Can you see my screen, Norm? Yeah, we're good.
Yes,
okay.
I can. Sorry, I had my mic off. I can, thanks.
Wonderful. Okay, thank you so much, PTRC, for co-hosting this with us today. We're so happy to be part of this webinar series that you're hosting. And of course, we are neighbors, and we've worked hand in hand on the projects in Saskatchewan that have actually happened. So thanks, Dan, for acknowledging that as well. The International CCS Knowledge Centre is based, again, next door in Regina to the PTRC, and we were founded by SaskPower and BHP Billiton. BHP gave $20 million over 5 years to share the lessons learned of the SaskPower Boundary Dam carbon capture and storage facility. And the SaskPower seconded its, I was trying to figure out how to go forward. SaskPower seconded its employees. So we actually have the engineers and people who were instrumental in building this project. And the intent of that is to make sure that as we move forward and transition into net zero future, that projects aren't starting from ground zero. And so we want to ensure that projects like Boundary Dam and others take those lessons learned and make sure the next projects through iterations have better efficiencies, lower costs, etc. This is the Boundary Dam facility that I'm speaking about. On the farthest left, that is Unit 3. That's where the CO2 is captured from. We capture the CO2, all of the emissions from the flue gas. We have to separate them out. And Conway will talk more about this later. But essentially, on the right here, you'll see the carbon capture and storage facility. That's where we use a chemical to separate out the CO2. That it's stripped away. That chemical is recycled. It's called an amine. It's recycled back in that absorber tower. We strip it out in the stripper, and then we compress it into a supercritical state. It's almost like a liquid. So when it goes in the ground, it actually is not a gas. And that's really important. And you'll hear more about that from my colleagues. I'm going to stick to the government regulations and the atmosphere that we're seeing here in Canada as things are ramping up to meet a net zero future. So Conway will tell you a little bit more about Boundary Dam going forward. So here's the current state of the CCS sector in Canada to date. And so all of these projects actually received government funding. And I just want you to know that approval for construction of the facility of the Boundary Dam 3 facility occurred early in 2011, and construction began that spring. The total investment in the power units retrofit and carbon capture plant was about $1.5 billion. And then in October 2014, the Boundary Dam capture plant became the world's first utility scale, fully integrated post-combustion carbon capture facility on a coal-fired power plant. In fact, it's the world's only today on a power plant in the world. So that's a pretty big deal. That captured CO2 is used for enhanced oil recovery in a nearby oil field, as Dan mentioned, and also for test injection into that deep saline reservoir aquistore. Overall, the Boundary Dam 3 demonstration project transformed Unit 3 at the Boundary Dam Power Station into a long-term producer of more than 110 megawatts of clean baseload electricity, while demonstrating that enhanced oil recovery potential in a fully integrated process. And so you'll see here how government dollars, just like that Boundary Dam project, were issued early and where they had their impacts. So the same thing with the Shell Quest CCS project. You'll see $120 million came from the government of Canada. And then with a matching $754 million from the government of Alberta, we see Shell Quest has now captured over 5 million tons to date. The Weyburn-Midale CO2 EOR CCUS operations, which have been operating for over 2 decades and captured, and Eric will correct me, but I think it's over 35 million tons of CO2 to date, taking that CO2 originally from the United States and then coupling it with the Boundary Dam emissions, also received government support, as well as, of course, the Alberta Carbon Trunk Line, which is a fantastic example of the creation of a hub. And so what's happening in Canada now is the need to have a net zero transition, but also the addressing of a market barrier in that government support is needed to get these projects up and off the ground. So what does that mean, and what does that look like for, as we ramp up to have a larger carbon price, and what does it look like for government incentives? And I'll talk a little bit more about that as we move along. So just to touch on historical greenhouse gas emissions in Canada. So with the Canada's target, it's about 45% reduction in GHG below 2005 levels to get to 511 million tons a year by 2030. So that's a difficult target to try and meet. It's also announced a target to achieve net zero emissions by 2050. And so CCS is a component of this, obviously, because it's going to have big megaton impacts. And while that target is ambitious, in order to achieve those emission reductions with that magnitude, there needs to be accelerated progress in the commercial scale deployment of CCS across a wide variety of applications. So that includes power generation with coal or natural gas, industrial processes like cement and steel, and fossil produced hydrogen, for instance, in addition to potential negative emissions from bioenergy CCS and direct air capture. And so the fourth biennial report that Canada provides to the United Nations Framework Convention on Climate Change on progress towards its Paris commitments actually lists carbon capture and storage as a core climate mitigation measure for both federal and provincial governments. And furthermore, CCS is recognized as one of the measures offering the most significant impact on sectoral GHG emissions and estimated mitigation impacts for the 2020s and 2030s. So I just wanted to show you a breakdown of Canada's greenhouse gas emissions by economic sector. So you'll see here that sectors like the oil and gas sector, electricity, heavy industry, even some agriculture, these are the sectors that CCS can really apply to. Transportation, potentially it will have the interconnection if hydrogen is part of that equation. But reducing CO2 emissions in the electricity and industrial sectors can be done through many means, right? So electricity, you can have energy efficiency, but of course you can also have the use of emission reduction technologies like large-scale CCS. And as evidenced by the high emissions from Canada's oil and gas sector, the world is still very dependent on fossil fuels, meaning CCS is a critical technology to meaningfully reduce the emissions arising from their use as we transition into a cleaner future. So I won't belabor on this slide because I know that Eric will do a very good job of talking about sequestration opportunities. But what I really want to show you is that in Canada, there is beautiful, beautiful storage opportunities that pair very nicely with where the emissions actually are. So the International Energy Agency's CCUS and Clean Energy Transitions Report, which was released last September, states that in order to reach a sustainable development scenario out to 2070, over 10 billion tons of CO2 has to be captured, and 90% of it must be stored. Only 8% of it is going to be used in other applications. And if you want to go faster to get to net zero by 2050, the world's going to need even more CCS in the energy mix, including more bioenergy CCS and direct air capture, with over 8 billion tons to be captured in that time frame and storing 200 times more than current levels. And here in Canada, the geological landscape has the capacity for a large volume of permanent and secure CO2 storage. This means that we're going to capture CO2 produced by these large industrial plants and compress it for transportation and inject it into these deep rock formations and at a carefully selected site, which PTRC can help you out with. And you know, you're going to need to look at those things like depth and location, containment, capacity, and those types of things. According to the CO2 Storage Resource Catalog, which has compiled global storage potentials, Canada has storage resources of almost 400 billion tons in these deep subterranean geological formations, the basins. In Western Canada, it's almost all of that. It's about 390 billion tons of that. Out east, there's only about 8 billion tons, and some of that's under the Great Lakes, so that's a bit difficult, a bit tricky. But all of the identified basins also extend into the United States. So, you know, geological mapping of sinks shows that there could be some opportunities in the United States and going across borders. And we know all about crossing borders for CO2 because we see that in Weyburn. So I want to talk now about the economic impact of a CCS project. So things like incentives can spur many projects with far-ranging economic and environmental benefits. And with those ample sequestration opportunities I just talked about in Western Canada in particular, this is ideal. And it's compounded by the current realities of idle resources stemming from oil price decline as a result of the pandemic. And so when we look at this, we see we're taking numbers actually from Boundary Dam and projects that have actually existed. For just 3 CCS projects over a 4-year construction timeline, there could be a 2.7 billion GDP from direct, indirect, and induced jobs. That's over 6,000 total jobs from just 3 CCS projects, which, depending on how much you're capturing and large scale, of course, you could be getting up to 5 million tons depending on which project you're targeting. So these are great opportunities to reduce emissions. The construction, so of those jobs and the economic impacts more broadly would occur in regions where large-scale CCS projects have, factors encouraging the likelihood of development. So like Alberta, Saskatchewan, even British Columbia. And those induced impacts are impacts from spending, employment, income, et cetera. At Boundary Dam, there were, I think it was 60 different contracted companies and no lost man hours in this. So it was really an important project to show the jobs in the community. And in Estevan in particular, this is something that people continue to work on to this day, as well as the maintenance from these projects as we continue to go forward and have regular shutdowns, et cetera. So I think this is what most people want to hear from me about, and it's what's happening in Canada in terms of new momentum and moving forward. So in Canada's budget, it was the first time carbon capture and storage was announced. And so they actually started talking about different opportunities for an investment tax credit. So south of the border in the United States, there is a tax credit called 45Q, and the Knowledge Centre actually helped with the design of this with Senate staffers in Washington, D.C. And from that, we also in the fall produced a report called Incentivizing Large-Scale CCS, recommending how a tax incentive could look in Canada. We're very pleased to see that our recommendation is one that also others agreed with, and it is now proposed and is having consultation periods as an investment tax credit over this, it's a 90-day time frame. You can check out our website for more information about that in particular. But as we look at what the Canadian budget is promising, some things start to, come to the surface. Who gets that credit? We really think that those eligible expenses should be described as the capital for a carbon capture project because these projects are so expensive. Transport and storage are also very important as a full chain piece of this. And they should receive government support as well. If they can't get an ITC, I think that maybe, SIF funding, strategic innovation funding, or Canadian Infrastructure Bank funding, all of these other things, there's different layers and different opportunities that are really popping up for large scale CCS to get us at least to 2030, when the carbon price may or may not reach $170 a ton. So the next piece that we also look at is emission reductions and timelines. We think that, in order to spur investment, that there should be a cap on eligibility for these projects. So they have to have a final investment decision for their project by the end of December 2029. Now, it could be extended into the future, but putting a cap on that time frame makes sure that it'll incent projects to occur in the near term. We don't think that there should be a cap on project numbers, emissions reduced, or even on dollars issued, because then people are not sure and it creates uncertainty. Projects that occurred before the release of the budget, we also think shouldn't qualify. Some of the things on investment tax credit design, we also think that because of the capital intensive nature, the ITC, investment tax credit, is a great idea. And that credit should be structured as a refundable capital tax credit that's issued as close to the time of spend as possible because of time concerns about the time value of money and things like this. The value is a big one. So this one's really interesting because without greater certainty from engineering design studies, those front-end engineering design type studies or feasibility studies, et cetera, project costs are really difficult to estimate. And without knowing project cost estimates, budget dollars can't really be estimated. And there's been a range of suggestions that stem from 75% of costs having to be covered by the government to like less than 50, maybe as low as 30%. But it really depends on the CO2 concentration emitters. So like the higher CO2 concentration, which is easier to capture, and Conway will talk more about this, they say, oh, we don't need as much money, which makes a lot of sense. Some of the oil sand companies, they're looking at about 75% that they're wanting to receive from this tax credit. And it doesn't have to be just from the tax credit. It's with any stacked government support. So if you can get some tax credit, some infrastructure development money, some ISED money from strategic innovation funding, maybe those things can all help. So maybe I'll just leave that slide at that, conscious of time, but please do take a look at our slides, because this document on our website that talks about key messaging. If you're going to put in a submission for the consultation period, take a look at that first. It's your first place to go. And we're also happy at the Knowledge Center to help you walk through it more. The last thing I want to talk about is certainty and risk. So what we're hearing from a lot of people is that, how are we going to do these CCS projects in Canada? There's a competitiveness issue with the United States. If Carbon Engineering, for instance, a fantastic Canadian direct air capture company, goes down to Texas because they can actually get money back, with the 45Q credit, which is $35 a ton for enhanced oil recovery and $50 a ton for permanent sequestration through production tax credit. It's a little different than the investment tax credit. So people might move south of the border to get, these credits back. The same thing happens with uncertain carbon pricing. And so risks on these projects, these are expensive projects. You don't necessarily want to always take the risk. There's some other low-hanging fruit sometimes, like fuel switching, et cetera. And so when you have certainty in the budget of an investment tax credit and different capital financing, what we're seeing is that companies are actually parceling those two pieces almost into two different pockets. So in terms of capital and outlay for capital, those certainty of the investment tax credit, capital financing like the SIF dollars I mentioned, and the infrastructure bank dollars, et cetera, that gives more certainty to build the project. The uncertainty around carbon pricing, clean fuel standards, different things, offset credits, that's really looking at the revenue now and the operating costs. It's becoming less of a business case to make things move forward because of uncertainty. Once things firm up and are more certain, I think that you'll see that there's less of a need to have certainty from government capital financing. So that speaks to the changing business models. So for projects in Canada to date, almost all of them use enhanced oil recovery as a way to get the revenue back from that oil, with the exception, of course, of Quest, because they had double offset credits that could make up for that cost. But as we move forward, if we can stack different credits, there's going to be different creative business models that we are looking at as we proceed. And what's really interesting is the government of Alberta has actually recently put out a pore space tenure management. It's going to be an RFP as it moves forward, but basically they're looking at having a public good in sequestration hubs. I think this is fantastic to add certainty for emitters who don't necessarily want to be involved in a full chain of carbon capture and storage events. They can focus on production of their cement or production of their material, whatever that may be, power. And then they can ensure that there is a long-term, less risk in a government approved, I suppose, public hub for the sequestration option. So I think that actually adds a lot of certainty as well, and changes the business model as well for a lot of people. EOR, really does have real reductions, and we see that on the life cycle as a total, there's 37% less greenhouse gas emissions than conventional oil. And the CO2 that comes from like a boundary dam, it is permanently sequestered where that oil was. But in the budget, EOR has been specifically said to not be qualifying for an investment tax credit. Of course, it is consultations, and I would encourage anybody who is an advocate of EOR to still ask for ITCs to include that. But that EOR uncertainty is creating a lot of uncertainty and risk in what those operations look like moving forward. I think clean fuel standards, though, could potentially make up for some of that. And so we need to make sure that those are done correctly as they move forward. The last thing I'll talk about in the presentation is technology readiness levels and near-term projects. So if projects are going to be deployed by 2030, there are a lot of new and exciting technologies in Canada that are up and coming. However, none of them really have a technology readiness level of what I would call an 8 or 9. So essentially proven technologies that have already been done. And so I think we need to ensure that there's still R&D dollars that are going into Canadian technologies to get them to a point where they can be deployable. But if we're going to have megaton impacts in the near term, we're really going to need technologies that are proven, as well as, ensuring that there are projects with proven sequesters, proven monitoring, all of those types of things that we need to ensure these projects are successful in the near term. So with that, I will end, and thank you so much for having me here today. Happy to answer any questions.
Thank you, Beth. Go ahead, Conway. I think we'll just go right into your presentation.
Sounds good. I will just get my screen shared here. Is that working?
Yes, it is. Perfect. Thanks.
Perfect. Great. Well, thanks for that, Beth. And so I'm going to touch a little bit on kind of what you need to think about to develop a CCS project in the spirit of, so you want to do a CCS project. I'll talk a little bit about what needs to be considered as you embark on this. They're major projects, and there are a lot of things that people need to think about before kind of jumping into them. So that'll be the focus of my chat here. There we go. So there are three different things that we kind of think about when we're looking at the kind of preliminary stages of a project. Kind of the high level cost and benefit comparison. Is there a business case? Is it worthwhile for the developer or owner? Are they going to save money by making this investment? Technology readiness level, which Beth mentioned at the end of her presentation. I'll talk a little bit about that. And then we're calling it project overview. It's sort of this is really that site characteristics. What are some of these specific things, some of these variable costs that you need to think about for a specific installation? There are some fixed costs and some variable costs, and I'll get into that a little bit. These three factors, we talked about this a little bit in a document we just released maybe a couple weeks ago, a need for feed document that's kind of an addition to some of the work that Beth's been doing on the investment credit. So there's some more information on our website as well if you want to dig into that a little bit. I'll move to the next slide. So the business case side of things. This is pretty basic. I mean, everybody knows to have a business case, you need benefits and you need costs, and you just do the math essentially. So some of the benefits for a CCS project are the obvious one, the carbon tax avoidance, that sliding scale of carbon tax up to $170 a ton by 2030. It's a pretty significant benefit. Various owners, developers may have some emission reduction commitments and obligations, and it's just something that has to be done. It might just be absolutely necessary. And some of the incentives that Beth touched on as well. There are some incentives available which show up sort of on the benefit side of the equation and help that business case. And then on the cost side, it's the standard. You've got your capital cost and you've got your operating cost. You have to factor both in and make sure that it's a sound investment for your corporation. So technology readiness level, or TRL. So this is something that we really look at for these technologies to make sure that we're not blazing new trail. When you're making an investment in the hundreds of millions of dollars, you want to make sure that the technology you're putting forward is somewhat proven. There are many people around the world that are researching new and kind of emerging carbon capture technologies. We're keeping abreast of those emerging potential game changers. But by and large, you don't want to start with those sort of lab scale or research scale technologies. You want something that's been proven and demonstrated, and that's really what we recommend to people as they're embarking on these projects. So essentially, there's a scale here from 1 to 9. really wouldn't recommend anybody going forward with a project with anything lower than an 8 or a 9 in terms of proceeding with that kind of investment. And as I said, there's a lot of research underway, and the higher the TRL number is, the lower the risk is in terms of embarking on a project. Yeah, I think that's enough on technology readiness level. So the project overview piece, these are what I refer to basically as variable costs. So there's some fixed costs and variable costs. Some of these things will change based on your application, and that could have a pretty big impact on the economics. So the layout of the site. Are there any integration opportunities in terms of adding this carbon capture equipment on site? Are there things you can connect to in the existing facility that can reduce, the parasitic load? I saw a good question about parasitic load for BD3, and I'll touch on that here at the end. Availability of utilities, there are some requirements to make these tie-ins, and do they have enough capacity? If you need to rebuild your electrical supply system to get enough power into the facility, that's a big cost impact. The composition of the flue gas, every process has a slightly different kind of recipe in the flue gas as it comes out, and they require higher or lower rates of pretreatment, and that can affect your cost significantly. Impact operations. Do you have the right skilled staff to operate this equipment going forward? Are they familiar with the equipment? Is there a big learning curve? All those are factors that need to be considered as well. So I'll dive into some of these in the subsequent slides here. So this picture will look familiar. Beth had the same photograph up in her in her presentation. But some of these variable costs, site-specific considerations, the proximity to the flue gas source. So as Beth mentioned, this is where Unit 3 is in Boundary Dam, 3, 4, 5, 6. We're capturing the CO2 from Unit 3, and this is the capture plant over here. So here's the absorber equipment, and here's the CO2 compressor. So this right here is a duct that goes all the way from the old stack that's not used anymore, essentially, over to the carbon capture. So it's about 270 meters long. So we had to build a big pipe rack and build this giant duct. There's also a 3-foot steam pipe that takes some process steam from the turbine in Unit 3 over to work with the heat exchangers in the carbon capture plant. Also had to build this the cooler out here, essentially for the process. It needed to be close to the reservoir, so it's located a fair distance away from the capture plant as well. So all of these things, if they could be right tight to the stack, could have reduced the cost for Boundary Dam Unit 3. So it really is something where you have to study the layout of the actual facility and figure out what some of these variable costs are. They can have a pretty significant impact on the overall capex for the project. So this one has to do a little bit with sort of that recipe of what's in the flue gas. I won't go through these in detail. You can kind of see the numbers on the slide there, but depending on the combustion source, the source of the CO2, be it a coal-fired boiler at 10 or 15%, the natural gas turbine 4 to 5%, the process from a cement kiln a little bit higher. Essentially, the higher the CO2 concentration is, the easier it is to capture with a post-combustion process. So your equipment can be a little bit smaller because the volume of the actual entire stream of flue gas to the volume of CO2, that ratio is in your favor. So I call those fixed costs, the cost of the size of the absorber tower, the regeneration tower, those things. It's just really the equipment supply cost, and the size is very much related to the amount of CO2 in your flue gas. So those are fixed by the kind of the recipe of what's in your flue. Some of the other things to think about when this comes up is the level of pretreatment required and what's in the flue gas. One of the major things we've learned at Boundary Dam is particulate is not our friend. You burn coal, you produce fly ash. Fly ash particulate is somewhat difficult to remove 100% from the flue gas, and it's caused us a lot of problems in terms of operations, amine degradation, pluggage, fouling, those sorts of things. We also have a high enough level of sulfur in our flue gas that the sulfur needed to be captured before we could go after the CO2. The amine technology prefers sulfur to CO2, so the sulfur has to come out first before we can get at the CO2. There are some other applications, ethanol plants for one. The CO2 that comes out, it is quite pure. It doesn't need a lot of this pre-treatment, so the economics look a little bit more favorable in terms of that capital investment. Yeah, I'll leave it there, but yeah, definitely something to consider is what's in your flue gas, and what do you have to do to clean it up enough so that you can get this relatively pure stream of CO2 ready for compression and subsequent storage, which Eric will get into. Another thing to consider is impact to operations. So one of the things that we did at Boundary Dam is we brought a totally new kind of foreign technology into a coal plant. We've got a lot of really good operators and maintenance folks that are very good at operating a conventional coal plant, but we brought in a chemical plant. So they're figuring out how to do this. They've gained a lot of knowledge. We did some upfront coaching and training, and I don't think you could ever do too much of that, especially when you're introducing something new. And some of our conversations with our friends in the oil and gas industry, they won't have that same sort of challenge with an amine process. They're already quite familiar with that technology, so that's an advantage for those sorts of groups. But one word of caution is to make sure that your operations folks are as prepared as they can be. So front-end engineering design studies. So Beth talked a little bit about feed studies, and this is a very critical step. And I mentioned that need for feed document we put together a little while ago. It's important to really characterize your site quite well and have a really good understanding before you jump in and make that final investment decision and commit to these hundreds of millions of dollars projects. They're major projects, and they require some upfront work to make sure that you're making the right investment, essentially. So I won't go through this table. You may be familiar with the cost engineers. This is a pretty widely accepted table in terms of estimate classes. Class 5 is really kind of high level, almost thumb to the wind. Class 1 is you're down super tight. You've got bids in place, and you're very accurate in terms of your overall project outcome, right? So plus or minus 3% to plus or minus 10 to 15%, so extremely tight. And there's a whole spectrum here. What we generally talk about to make a final investment decision, and this is what ACE is talking about here as well. Budget authorization. This class 3 is kind of typically where people try to land. So your project is defined up to 10 to 40%. So the level of engineering completed is in that 10 to 40% range. And our experience at Boundary Dam 3, we actually went a little bit beyond class 3. We were more into kind of a hybrid between class 3 and class 2, where we had the engineering probably close to 50% done, and procurement processes that started with some of the major contracts. So a little more certainty in terms of some of those contracts, and that can bring your estimate accuracy down a little bit tighter. So it helps with that investment decision. But that's generally what we like to recommend. I don't think anybody would want to go forward with a $100 million plus decision on a concept screening level estimate. It's really important to go through this feed study, characterize all those variable costs that I talked about in previous slides. It's really important to understand those and make sure that you're comfortable going forward, and minimize surprises essentially as you're executing your project, which nobody likes. So one of the things that we've learned from Boundary Dam Unit 3 has a lot to do with the integration piece. You'll recall I talked a little bit about the potential for integration with the existing facility. The Knowledge Centre did a study on our Shand unit. So it's just down the road from Boundary Dam. It's a 300 megawatt plant, so twice as big as the BD3 unit that has carbon capture on it today. And really just to look at, okay, we've done Boundary Dam Unit 3. What can we do differently on Shand to bring the cost down? And really found a lot of really very promising improvements. And the next slide goes into that a little bit, but I will mention we collaborated with Mitsubishi Heavy Industries, Mitsubishi Hitachi Power Systems, SAS Power, and obviously the Knowledge Centre. Mitsubishi Heavy Industries is a post-combustion carbon capture vendor, essentially, someone you can purchase this equipment from. They have that expertise. So the Shan feasibility study, again, 300 megawatt coal units, projected carbon capture of 2 million tons per year, so twice as much as the 1 million ton that was the target for BD3. Capital costs were, what we're finding, it can be 67% less per ton of CO2. So not 67% less than capital cost for a plant half its size, but per ton of CO2 captured, a significant capital cost savings. Cost of capture comes in around $45 US per ton CO2. So when you compare that to the current carbon tax pricing regime, it's quite attractive, even without things like enhanced oil recovery. Capture rate up to 97%, not dissimilar from BD3. And fly ash sales are another thing that can reduce that CO2 footprint. But the real savings here, the real thing that we uncover is just more integration in terms of waste heat from the power plant and utilizing that waste heat in the capture facility. There's some major opportunities there. So one of our active projects right now that we're working on is working with Lehigh Hanson, their facility in Edmonton. The cement industry is an interesting study where they've got, they have emissions that are based on their process. So there's really nothing they can do in terms of changing their heat source or their fuel source. These process emissions essentially need to be captured or pay the tax. So we're undertaking a feasibility study right now, partnering with Lehigh, partnering with an EPC contractor, Kiewit, partnering with Mitsubishi Heavy Industries again on this study as well. The study will be completed at the end of September, and it's also funded by Emissions Reduction Alberta. So about 50% of the cost of the feasibility study is funded by the ERA in Alberta. It's a fairly significant project, 780,000 tons of CO2 annually, so almost the same size as BD3. And the expectation is the end of September, we'll finish this feasibility study. We'll move into a FEED study, as I was describing earlier. Everything looks quite positive for that project right now. It's been quite interesting for us. This is the last slide I had, and this is the overall. This is just I like this graphic. It's a good picture of the overall carbon capture and storage piece. A lot of our experience is more so tied on the carbon capture side of it, and I think Eric can talk a little bit more about the storage and the enhanced oil recovery piece of it. But what I like about this slide is it's really this source of CO2 can come from any industry. It can come from the cement industry, as I just talked about with our work on with Lehigh Hanson, the steel industry, natural gas, coal power, any sort of source of CO2. What we've done at Boundary Dam Unit 3 is we're able to sell a lot of the CO2 for enhanced oil recovery at this kind of higher elevation. In order for us to have the permanent storage, we're going quite a bit deeper. And again, Eric is the expert in that area. That's really what I wanted to touch on. And I think the thing that I'll just leave you with is it's really making sure that you do a good job of analyzing your specific facility, your specific business case. What sort of integration opportunities do you have? What are your fixed costs? What are your variable costs? And get into that front-end engineering design to make sure that you've got some good certainty when you go to your decision makers to proceed with the project. I do have one more slide that I'll just show just to touch on that question about the parasitic load. So this is just a high-level overview of Boundary Dam Unit 3, but Norm captured it quite well, actually. So the compression cost, so the cost of running this major CO2 compressor to get that CO2 to a supercritical state is about 14 megawatts. And the station service for the capture plant, so all of the other pumps and heat exchangers, all that equipment, is about 11 megawatts. So 25 megawatts of parasitic load is what we're dealing with. The original Boundary Dam Unit 3 was 150 megawatts. When we have it already had a station service load, so essentially its net output was 139 megawatts. So really we're coming down to 110 when everything's said and done. So our total parasitic load from carbon capture is about 25. The overall parasitic load from other station service is about 55. So, answer that question. And with that, I will hand it off to Eric.
Okay, great. Go ahead, Eric. We're a little bit behind schedule, but that's all right. That's usually the case in webinars. So you go ahead, Eric.
Great. Thank you, Norm. My name is Eric Nickel. I'm the Director of Operations at the Petroleum Technology Research Centre. And I talk about not EOR so much as pure storage at this point. You know, we're getting a lot of interest from various companies on just what it takes in order to do this. Here's just a little bit of background for you on what we'd be looking at. Advance. The PTRC, a little bit of background. You heard Beth talk about the Weyburn project and Aquastore. The Weyburn project has stored, it's actually close to 40 million tons if you take the Midale field into there as well, 40 million tons of CO2. What changed that from a CO2 EOR project to a storage project? We're going to get into that. Aquastore is our current premier kind of project that we have on the go that is a deadwood, essentially a disposal well. But again, what makes disposal, what's the difference between disposal and storage? And let's talk about that a little bit coming up here too. We've put almost 400,000 tons of CO2 into that well now. So you want to drill this disposal well, and I put disposal in quotes. Of course, you need just what the previous folks just talked about. You need the economics to work. You got to capture something. You got to transport it, either pipeline or truck or something. And you need to acquire the land or the pore space, as you're going to hear about after me. Next thing you need to do is select the site. And that's not just a geological process, but surface one as well. Then a very important step that people often forget about is a risk assessment, because this risk assessment and the results of it informs everything else that comes after. The design of your well, what you want to monitor on the well, what you want to monitor on surface, what data you want to collect during drilling, and how you communicate all of that to the public and why that is important. So this is kind of also serves as a bit of an outline for the talk today, but I will be brief. Site selection. Of course, there's geologic considerations. Beth pointed out very conveniently that in Western Canada, we are blessed with a lot of pore space, thousands and thousands of kilometers of very thick material like the Deadwood Formation here in the Cambrian, the oldest sedimentary formation in Canada. It is true that it is present throughout the West, but you do have to know where it's not present, which is in these, you know, very small sort of discrete areas where this is a deadwood thickness map, where suddenly it goes to 0 meters from where we're at Aquastore, 140 or thereabouts meters, to 0 if we were to drill this thing 40 kilometers to the northeast. That's just one of the geological considerations you have to have in mind when you do this. There's also other things other than the deadwood. We also look at storage in the Black Island and Icebox, which are part of the Cambrian or Ordovician Winnipeg Formation as well. These are the overlying Mesozoic beds that serve as the sealing units for the underlying CO2 storage. What you'll want to do when you do this is create a model that shows where you're going to be in 2, 4, 10, maybe even 100 years out in terms of plume size, plume thickness, which beds are taking more CO2 than the others. This is the one we initially did for Aquastore, and it serves as a pretty good proxy, or looks pretty good to what is actually happening down there. You use as much geological information as you have, recognizing that you're going to be short in a lot of ways. But also in site selection, there are surface considerations. This is a satellite view of the Boundary Dam site. Right here is the power plant that Conway was just showing you. The red line is the pipeline that goes to the north, then the west, and then it doesn't show it here, but off to the northwest to Weyburn for sale. There is a little metering station here, and some of this comes down to Aquastore. Now, why did we choose this location? It was geologically, it worked, but also it's close enough to the power plant. It's not situated in a lake, and it is on Sask Power owned land. So that becomes a very important consideration as well. Who owns not just the mineral rights or the pore space, but who owns the surface as well? Because you're going to be out there quite a lot and installing surface monitoring equipment. Next thing, after you have a good idea of your geology, would be a risk assessment. And the risk assessment is a systematic process by which event scenarios We used to call them FEPs, or features, events, and processes. So if you think up some kind of thing that is going to cause risk or harm to your project, and you consider that event, you consider how likely it is to happen and how critical or catastrophic it is if it does happen. For example, a well blowout, catastrophic thing that would happen if your well blew out suddenly, but it's highly improbable that that's going to happen given all the mitigation factors you've taken into that. An extreme weather event would be another marginal effect on it, but something that's probably going to happen in Southeast Saskatchewan. You're going, you know, Boundary Dam suffered a tornado spinning right next to it, and you know, things happened, and the well survived, and everything was fine. But it's a risk you need to consider. So you go through literally hundreds of these scenarios. They're not just technical things. Sometimes they're economic, sometimes they're public relation related. They can be anything, but from this you develop a risk management plan, which then goes on to inform everything else you do from this point on. You want to take baseline monitoring measurements. So this is again the Boundary Dam site, and these are all the soil gas measurements of the different gases within the soil in that area, complicated by the fact that the area we chosen was formerly a coal mine. You know, it's mine tailings that have been flattened out and redeposited there. But all of that coal has been stirred up, so it's not exactly the same as the surrounding farmland. You have to take that into account. Likewise, with the groundwater, you approach not only wells in the immediate vicinity, but those of farmers and so forth around as well. And investigating the different types of ions in there, then you'll know if there's a change coming. Likewise with INSAR. INSAR is a really interesting technology that uses a satellite to tell if you're changing the Earth by injecting something into it by there being a bulge, for lack of a better term. Highly unlikely that that bulge would ever occur when we're injecting 3,000 meters plus underground, but it's possible nonetheless. But you have to then also be aware that the entire continent of North America is rising after the melting of the glaciers, and also some dropping in relation to the settling of those mine tailings that I was talking about. So all kinds of things to consider, including with passive seismic. We have seismometers out there, ensuring that we're not inducing any earthquakes, but also filtering out earthquakes that might be related to potash mine or something that happened in Indonesia on the other side of the world that we're picking up here. So the well design also is informed by the risk assessment. What do you want to make sure that you capture? This is the well design of the injection well and the observation well, which are 150 meters apart at Aquastor. The injection well is a fairly typical, what you would call a disposal well, a casing with tubing down the middle of it, a packer set just above the zone of interest, and then perforations, and CO2 is injected down this tubing and goes through the perfs. But what's special about this well is the amount of jewelry or the amount of monitoring that we have on it. We have tubing conveyed pressure sensors, and we have casing conveyed pressure sensors above the zone of interest to ensure that we're not pressuring up those zones outside of the well. We also have fiber optic lines that on the outside of casing serve as temperature sensors to see if there's a change in temperature anywhere, which would be your initial indicator of a leak of CO2, would be a drop in temperature, because the geothermal temperature of these formations is much higher than that of the CO2 that we're injecting into it. There's also fiber optic lines on the tubing that that can and have given us advance notice of leakage into the annular space. On the observation well, it's similarly instrumented, but it is much more simple. There's no perforation in it, so it's not accessed by the reservoir at all. There is casing conveyed DTS and DAS lines. That's the fiber optic lines that give us temperature and acoustic sensing. So we're listening for those earthquakes we might be inducing. But also a fluid sampler down here that's on the outside of casing that gives us little samples of the reservoir fluid. Now, does every project need all of this stuff on their wells? Likely not, but it is, again, informed by that risk management plan. So Despite all of these challenges and despite all this worry about is there going to be enough deadwood there, the wells were drilled regardless. And there is always going to be some risk. It's just how comfortable you are with accepting it. But in the summer of 2012, we drilled the 2 wells. And this is what the wellhead looks like. It's a fairly, for those in the oil industry, it's a fairly typical looking wellhead. This is the pipeline coming into it. Here's where it comes out of the ground from Boundary Dam or from that metering station, goes through a little building here where it's measured and the pressures are measured, and then out and down the well. You can see these lines here are the fiber optic lines that are running everywhere and continually monitored. And this rack full of nitrogen here is to keep that annular space pressurized, and so that we're not generating leaks. When you have all that, you get to enjoy fun plots like this that look at the varying injection pressure and injection volume as the BD3 plant had on startup, and what that does to your well, changing the temperature profile of it greatly. When you're injecting lots, the whole well cools off. When you're not, it heats up. What does that do to the geomechanics of the rocks underneath? Interesting questions, but always ready to give you answers if you do find a leak or how to best to mitigate a leak. So lots of fun stuff can come from that. At the end of the day, this is all about public assurance, meeting the needs of what the regulator wants. What they want to hear at the end of the day is that you've had 0 impact on soil gas or groundwater, or that you're not creating any seismic activity. And here's how we can prove it with all of these different systems that we have in place. Communications then becomes the most important thing, to communicate that fact to the public. With Aquastor, we held these seminars that we invited the people, all the public from Estevan to come to get an idea of all of these aspects of CCS. Just like what we're talking about today with a professional audience, we would do the same with the stakeholders, the landowners, the townspeople, just to make sure that everyone is on the same page and knows what we're doing, because we have absolutely nothing to hide when it comes to this sort of thing. So to sum up, the considerations that you would also have, the amount of core you want to take as a geologist, I'm going to say the more the better. The logging program, allow for repeat loggings like a pulse neutron density that allows you to track the concentration of CO2 in your formation. Make sure there's a communication plan in place. Most of the CCS projects in the world, especially in Europe, have failed because of public outcry, because of a lack of communication. So it's a frustrating thing when you have all these brilliant engineers and scientists working on this problem, and it gets completely shut down by misinformation. And it always comes back to that risk management plan that you develop early in the process. So what's the difference between disposal and storage at the end of the day? It is all of that monitoring that we put in place and those assurances that we're able to give to people about what we're doing there. And with that, I will let you guys learn a little bit more about the tenure and acquiring the pore space in order to do all this fun stuff that I just talked about. Thank you very much.
Thank you, Eric. Yes, Jing Zhao, you're free to share your screen and start your presentation. Yeah, it's working.
Screen here.
Yeah, works good.
Hello, everyone. My name is Jin Zhou, Manager of Disposal Well and Storage Projects with Energy Regulation Division at Saskatchewan Ministry of Energy and Resources. First of all, thanks everyone for attending this webinar, and thanks to the speakers from PTRC and the International CCS Knowledge Centre. Next, on behalf of the Ministry ER, I'm going to talk about the current Saskatchewan legislative and regulatory context on the injection and the storage of CO2. We may have different audiences today, so I will give you an overview of the ministry. Then I will introduce the key acts and the regulations, as well as directives administered by our ministry. I will also mention other jurisdictional roles in regulating CO2 projects. Then the CO2 project and the well permitting process will be highlighted. Next, where you can submit your application and where to find additional information. The Ministry of Energy Resources develops, coordinates, and implements policies and programs to promote the growth and the responsible development of the province's natural resources industries. The ministry operates as the primary regulatory authority for the oil and gas industry and ensures competitive royalty systems, regulations, and policies for all natural resources sectors. The ministry also plays an important role in promoting Saskatchewan's diverse resource potential to investors around the world. The structure of a ministry reporting to the deputy minister, we have major 4 functional areas. The strategic planning and initiatives branch ensures organizational change through delivering strategic priorities. Revenue and business system provides oversight of the integrated resource information system, IRIS, as well as financial part of non-renewable resources revenues. Resource Development Division advances policies and programs that encourage the development of the mining, energy, and the forestry sectors. And last, Energy Regulation Division develops and implements the responsible regulation of Saskatchewan oil, gas, and associated mineral resources. RDD, the Resource Development Division, is responsible for the Crown Mineral Act and the Oil and Gas Tenure Registry regulations. The Crown Mineral Act defines that the ownership of pore spaces on Crown mineral lands has been vested with the Crown. The minister may enter into agreement to lease spaces. Currently, the government does not claim the ownership of pore spaces on freehold lands. The Energy Regulation Division is responsible for the following acts and regulations. The first one, Oil and Gas Conservation Act and the Oil and Gas Conservation Regulation. The OGCA regulate the injection, storage, and the withdrawal of substances into or from subsurface formations, including, in this case, non-oil and gas substances, for example, CO2. And we also have Pipeline Act and the Pipeline Regulation, which apply to pipelines only within the Saskatchewan boundaries. It provides for the licensing of CO2 pipelines, and the regulation also incorporates CSA standards Z662. In order to conduct or permit seismic program in Saskatchewan, a company requires the license to conduct seismic exploration. And the last one, the Surface Rights Acquisition and Compensation Act and its regulation, regulate the relationship between the landowners and the mineral rights holders respecting to oil and gas and the potash development activities. Directives is a very popular form of regulatory instrument to establish rules and guidelines on technical requirements. Currently, the ERD, we administers a total number of 29 different directives for oil and gas activities, which are performed throughout all phases of the resource development, such as construction, operation, measurement, and reporting requirements. You can access to all of this directive through the Government of Saskatchewan website. Other provincial jurisdictions, such as the Ministry of Environment, also have roles in certain oil and gas projects. In particular, ENV, that's Ministry of Environment, handles environmental reviews for some upstream oil and gas sites and pipelines. They regulate midstream and downstream oil and gas infrastructure, such as refineries, and currently the CO2 capture facility as well. And the overseas responses to oil and gas incident having environmental impacts to fish and wildlife. Permitting of oil and gas project is governed by a number of legislation and regulation with the Ministry of Environment. The major applicable legislation include the Environmental Assessment Act, the Environmental Management and Protection Act, ENPA, the Provincial Lands Act. It is to note that the permitting requirements under ENPA and the Lands Act are currently integrated into our single window program in our licensing process. Next, I will talk about the CO2 and the well permitting process administered by ER. The province has two major miscible CO2 ER projects, Weyburn and Midale EOR, and one CO2 sequestration in Sanding Aquifer near Boundary Dam. There are a few of non-miscible CO2 EOR projects in the Northminster area, but just in a much smaller scales. This chart is a very simple process chart for a CO2 project, starting from planning to its termination. As Beth and Conway mentioned, once the project proponent completes the screening and the feasibility or FEED study, and the to-go decision is made, the CO2 project is defined as to the project area, the number of wells, the well density, and completion strategies. After acquiring the subsurface rights, which I'm gonna talk about later, and conducting public loaders as per ER's directive requirements, a project application can be submitted to ER in hours. ER then would conduct a full technical review and work with the applicant for supplemental information and clarification if needed. The project is authorized with a Minister order, MRO. The company will have to use project authorization number to apply for a well license. The facility and pipeline licensing process, they're separate process and are not included in the project authorization. By the way of licensee, the licensee is subject to all of the obligations associated with the project, the well, the facility, and the pipeline. And it is to mention that the project owner or operator should comply with other federal, provincial, and municipal regulatory requirements before the construction work starts. And then a project application might be needed for if you're gonna modify or expand your project after the initial project authorization, such as if you're changing a project area, you're adding or reclassifying wells, and the modification of the major operation conditions. A separate application for well repair if you got a failure problem, and for well abandonment is also required at the well level. All of the activities, the operations should ensure the reservoir and well integrity, complying with the OGCA and its regulations and directives, such as measurement and reporting, incident management and reporting requirements. I will briefly introduce 3 current processes that are highlighted in yellow in this process chart. They are how to acquire subsurface rights, how to apply for a CO2 project, and how to apply for a license. The CO2 EOR project will follow the current oil and gas tenure requirements. For example, you need a PNG lease on Crown lands. Pooling agreement are required on diverse mineral lands, and the agreement should be in place if you're injecting into freehold lands. For a CO2 storage project without EOR purpose, you will require a lease of spaces agreement, which is to enable access to pore spaces on Crown lands. The lease of spaces is administered by our Ministry, Land and Mineral Tenure Branch. It can be applied through IRIS under non-advertised disposition application. Lastly, consent is also required from freehold landowners as well. The CO2 project authorization. The application for CO2 project with or without EOR can be made through IRIS under different project classification. The Government of Saskatchewan website contains application guidance for both type of projects. However, they do have different requirements due to the differences of the primary objective and operation scheme. The project authorization also approved the proposed well locations. The project is authorized with the Minnesota MRO. The MRO will stipulate specific developmental and technical elements of project activities. For example, we will put a language in the MRO, say company X shall do this. MROs also have paramountcy over regulations. The well license can be only applied after the CO2 project is authorized. There are different well completion types for CO2 EOR wells and non-EOR wells. As I mentioned, the facility license and the pipeline license are separate from well license applications. They don't have to be applied at the same time. It's also should be loaded. Currently, ER does not license CO2 capture facility. For pipeline license, we have a map viewer module in ours, which can be used to enhance the interactive map-based experience for pipeline activities and provides a GIS map screen within the IRIS application for users. As I mentioned IRIS many times, here is a snapshot of IRIS screen. It is an online tool that supports the development and the regulation of Saskatchewan energy and resource industry. Through IRIS, the industry completes business activities and regulatory tasks online, including the application under the petroleum natural gas module for project application, enhanced recovery, and the CO2 storage project. And for the license, the well, facility, and the pipeline license. The petroleum tenure model then again is a place to apply for a lease of spaces, which I just mentioned before. Recently, we have also implemented some new features in ours, including the mineral ownership special records, phase 3, to enhance tenure and the well license application process. And just last week, the structured project application authorization feature to enhance the EOR application process. Here are some helpful resources related to oil and gas activities available at our Government of Saskatchewan website. Each of the sections include detailed information, application guidance, and application forms that I have mentioned today. So please visit our website frequently to check any updates. This is the end of my presentation, and for any additional questions or assistance, your inquiry can be directly sent to our toll-free number or by email to our ER service desk. Welcome if you have any other questions. If I didn't mention today in my presentation, I will be very glad to answer some of them. I guess I will stop sharing my screen and turn the webinar back to Norm for a question part. Thank you.
Thank you, Jean. So yes, we are. I'm very cognizant of time. We are up to basically the 75 minutes. There is one question that is still outstanding. We have been typing some answers to questions. I thought I would put it to whoever can actually offer this. And this is again from Dave Corvo. He's been asking some interesting questions. One was about why we don't talk more about CO2 being stored at under 1,000 meters. Eric wrote a fairly good reply technically, and that is that it's difficult to keep CO2 at supercritical levels at that depth. But is there a position, Jing, on depth for CO2 storage in terms of the Saskatchewan government? Do you have a specific depth that you require, or has that been discussed at all within the government? Do you know?
So currently we don't have a legal framework in terms of how deep the CO2 can be stored and what is the suitable formations. So to answer this question, I will say it's a scenario based. It's all based on your project proposal. What's your primary objective is for EOR purpose or is for sending aquifer storage. For EOR project, I believe the current EOR project, it's about maybe close to 1,000 meters or 1,500 meters deep. And again, it depends on your measurement, monitoring, verification requirements. And as I mentioned, the company should do the due diligence to do upfront feasibility study just to verify or to provide a scientific basis information in order to us to do a full technical review.
Right. Okay, so I will get to David's second question here in a second, but I thought maybe either Beth or Conway could answer. Boundary Dam 3, this is from GoCam. Boundary Dam 3 was cancelled. Shand is MHI. Is there a reason why that may be happening?
You know, and this happened before my time with the Knowledge Centre, the Shand study, but we would have done a request for proposals to pick a vendor, and MHI were interested in partnering with us in the study. So they're both reputable carbon capture technology vendors, essentially.
Okay,
and I shared the list of all the technology readiness level 8 and 9s. Well, actually all of the technology readiness levels in the answers, and you'll see all of them. Part of the other reason we used MHI was because they actually did the Petronova facility in the United States. And so actually taking their lessons learned from application on that other facility and applying them with boundary dam knowledge as well actually is what helped to show that significant increase of 67% per ton of capital. So that was part of the other reason, Norm.
Good, excellent. So the last question, and by the way, everyone, you're welcome to contact me at info@ptrc.ca. That comes directly to me. Again, that's info@ptrc.ca. If you think of a question afterwards and would like to send it. But we'll look at Dave Carroll's last question, and anybody who can answer this, it's interesting. Do we have any operating experience in repurposing depleted oil wells for CO2 storage? He's curious about public and regulatory feedback and or observations if available. Now, I know just peripherally that we did some work in the early days of the Weyburn project looking at a couple of the older wells in the reservoir and how they were affected by CO2, but they were not injection wells. So Eric or anyone, can current injection wells be used for CO2 injection in an oil field?
It's a very good question. Only to my knowledge in Saskatchewan, we have not. You know, there are very few CO2 injection wells here, and you know, if you look back at where I showed the well design of that, there's important things like CO2 resistant cement and casing in those wells. So the repurposing of old wells, I think, would have to be something that would need some study, I think, before it would be allowed.
Right. So the injection wells, Eric, at Weyburn, the alternating, the WAG wells, were built for that purpose, were they?
Most of them, but there were a lot of other much older vintage wells in the area, and you know, wellbore integrity on those wells, if they're used or even if they're just sitting there within the reservoir, is something that's important to take into consideration and monitor for leakage.
Right. Okay, well, I think we will wrap up questions. Thank you, everyone, for your patience. We went about 10 minutes over, but I'll maybe turn over to Dan for a few closing comments. And then, as I said, please feel free to contact me. The movie will be posted by Monday at the PTRC YouTube page. You'll get an email. And I'm not sure, but I think PDFs may be available from all the presenters. I'll check with the Knowledge Centre to make sure If there's links available to give people access to the PDFs of these presentations, I'll make sure that you also get that information. Go ahead, Dan.
Well, I'd just like to thank Beth, Conway, and Jing for participating. Thank you for your presentations, very informative. Thank you, Eric, again for your presentation as well. And to everyone who was watching this, again, if you have any questions or follow-ups, feel free to connect with Norm. And we'll see you at our next webinar. And hopefully we'll see you in Regina in May of next year at the Williston Basin Conference.
Thanks for having us today, guys. This was fantastic.
That was very good. Thank you. Your presentations were very interesting. Thanks, everyone. And thanks for attending our webinar. Bye.